Hello everyone, welcome to my YouTube channel. Today we are going to discuss about types of biomaterials. In previous class we discussed about tissue engineering scaffolds and various how exactly this particular scaffold works and how they mimic the property of ECM. All those things we have discussed, right? So in this video we are going to discuss about types of biomaterials. The most common classes of the materials used as biomedical materials are polymers, metals, and ceramics. So basically, the materials, okay, like in mechanical materials, they are classified as metals, ceramics, and polymers, right? So out of in biomaterials also same thing, right? So same in certain applications we need polymers, certain applications we need metals, and few applications we might need ceramics. So usually when we will need ceramics wherever there is much kind of whenever it comes to the brittle wear and tear applications and also lot of hardness, we will use ceramics and metals. Whereas whenever it comes to the soft tissues, like for example in angioplasty you might have heard where this particular heart valves will be there, those valves will be repaired, okay. So in these kind of applications, and also inside our human body, it's most of our cells are if you compare with any different materials except bone and certain tissues, rest all the tissues they resemble the property of polymers. So most of the applications, polymers will find more applications in the human body rather than the metals and ceramics. Whereas ceramics and metals play a very important role when it comes to the bone fracture or any these rigid structures are there, rigid cells or tissues are there inside our body. They play a very important. The metals and ceramics play a very important role to replace the damaged tissues, so the rigid tissues and all like bones, cartilage, all those kind of things. So these three classes are used singly or in combination to form most of the implantations devices available today. That means either I use only polymer, I use polymer along with the metals, or I use polymer along with the ceramics, or I use metals with the ceramics. So it depends on the application and what kind of what exactly the need of that particular patient, and depending on the patient's need we are going to use this material. For example, imagine a patient makes with an accident and he loses his his bone fracture will be there. Along with that, muscle fracture is also will be there, because when the person is obviously whenever the person is losing his this thing, what do you say, the bone, that means he is losing his most of its his cells also or muscles also. So muscles are already fractured there. So I need scaffolds, so which maybe most of the times it will be polymers. So I need for to correct to give support to these broken bones, I need metals or ceramics. So here I can use both polymers and ceramics. Whereas in some certain applications, for example in angioplasty or normal heart valves or the blood vesicles, if any rupture is there, then I can use simply I can use the biopolymers, so that I can because there we don't need metals and ceramics, understanding. So it depends on the patient's need and requirement at that particular situation. So based on that the things will change. So metal based polymer, let's discuss one by one. So first we will start with the metal. So metal based biomaterials. In 1920, with the introduction of stainless steel, it was considered that it has a far superior corrosion resistance to any metal at that time. So here this point is telling that when the 1920s, when stainless steel was introduced, so this has become a very significant material in every field, most of the fields, right? So even in biomedical field also it has got a lot of application. The reason is very simple. So when it comes to, when you compare any metals with stainless steel has got one property that plays a very important role. It has got a far superior corrosion resistance. That means you can keep it under, even though you might have seen. So most of the times your maybe it's your normal buildings or your home or maybe some institutes or companies or whatever outside you can see. So most of the times it will be the stainless steel, regarding these things only structures will be put. The reason is very simple. Even though it is exposed to a lot of rain or humidity or something like that, the corrosion will be very less there. Okay, so that's why it has got a far superior corrosion resistance to any metal at that particular time. So thus it was also adopted to be implanted on the large scale. That means it is used as implants rather than just metals. So since then the metals have been used widely as biomaterials, because only problem with the biometals using inside the body was the corrosion, because inside our body we know that it's like blood is flowing every time, okay, and we are having interstitial fluids and a lot of body fluids are there. So it's almost hydrophilic in nature inside our body. So most of the time it is kind of wet kind of situation inside our body. So it has to be corrosion resistant. The metal whatever you are keeping inside the body has to be corrosion resistant, so that it should not cause any corrosion. Because imagine we know that the bone fracture, whenever the bone fracture happens, we know that the bone fracture healing, it takes a lot of time. So it's not like the tissue generation or skin generation or whatever it is. It takes a lot of time in this particular, because it's a very rigid structure inside our body. So it takes a lot of time. So it takes a lot of time in the sense that whatever the rods you put as a metal rods you put in order to give a mechanical strength to the body. Okay, so to replace the damaged bone. So until that bone gets back to its original state, this metal has to be there. Right, understanding. So and sometimes for a lifetime it has to be there in some cases. Okay, so it has to be corrosion resistant, not just a corrosion resistant. It has to be superior corrosion resistance. That means it should not have any it should not be corroded after 10 years, 5 years, or maybe 1 year, whatever it is. So since then this the stainless steel was introduced, so it has become a very great what do you say field of interest, or interest of material to use as a as a implanting agent or implanting materials or metals. So metals are used as biomaterials due to their excellent electrical and thermal conductivity. So that's the major thing. And one important property, we already know that compared to the compared to the polymers, we have got this particular metals will have a great mechanical properties. So electrical, thermal conductivity and mechanical properties. Now the demand for major biocompatible metals such as, for example, stainless steel, titanium, chromium, cobalt, nitinol, gold and as well as silver is significantly increased owing to the increase in cardiovascular, orthopedic, dental and neurological diseases that require implants and the surgeries. So which use metals at at every stage. That means we need a different aspects are there. Different cardiovascular is there, orthopedic is there, dental and different neurological diseases also. In all these ways, we have got different materials that we need to keep on using since a century, I can say, because it's 1922, it's almost 2023. So most of the stainless steels and along with the titanium, chromium, cobalt, nitinol, gold and silver are significantly used as implantable materials for both implants and as well as surgeries. So some metals are used as a passive substitutes for hard tissue replacement. For example, like a passive substitutes, like a small substitute is for the missing or damaged tissue or damaged joints or a hip or something like that. So some of the examples are there here. Total hip for hip this thing damage. Next we are having knee joints, and for fracture healing aids as bone plates and the screws. You might have heard that the particular person has been put a bone rod inside him, or bone plates or screws inside him like that. So the spinal fixation devices. Then we are having dental implants because of their excellent mechanical properties and corrosion resistance, and vascular stents and as well as catheter guide wires. So we have studied this catheter guide wires, if I am not wrong. So for your angioplasty and angiogenesis and also angioplasty and all. So they use this particular during the angiogenesis topic. I might have explained you guys this catheter guide wire. We usually use it for whenever there is obstruction in the blood vessels, so that we can remove that, and vascular stents also. Okay. So that was about the metals. So where these vascular stents and guide wires are like as thin wires where we can use it for the tracking, or maybe vascular stents used to can be used to make sure that what happens in the blood capillaries, the blood will be flowing, right? So due to its what do you say, the fat accumulation, what happens, it might get blocked. Okay, now you will take certain medications, or you may undergo for some surgery to remove that particular block, or that cholesterol. Once that cholesterol is cleared, but because of that cholesterol bulge, so this walls, these capillaries will be bulged like this, right? So now once it is gone, now they will come back like this, and they will block the flow of the blood. So now we have to make sure that we have to create a bit stable gap there. So for that we will introduce a stent, vascular stents, or catheter guide wires. Also it will help the doctors to track it. So that's how the things will be used. Now that wire, whatever you are using, again it's again made up of stainless steel or some metals. So that's what here we are seeing. So that was about metals, and some of the importance of the metals, and some of the examples, and also some of the what do you say, the reasons where we use the metals. Okay, so next we are having the polymer based biomaterials. Whereas polymer based materials have replaced other materials such as metals, alloys and ceramics because of their low cost, chemical stability, easy processability, and reprocessability. Again we can use it, and better corrosion resistance. Since it is not metal, there is no corrosion itself. So these all are the properties which plays a very important role, and makes it's one of the, whenever it comes to all these properties, the polymer plays a very always takes over other materials. So the polymer based biomaterials have been extensively used in medicine, biotechnology, food and cosmetic industries. So there are a large number of the polymeric materials are there, so that have been used as implants or part of the implant systems. For example, I can use the whole polymer itself as an implant, or I can use for particular tissues or particular this thing, or I can use a part of the implant as a polymer. As I told you in the example of the bone fracture, so I use the metal for a bone plate. Along with that, for tissues I use as a support or something like that, or to cover this particular metal with which affects the tissues, the surrounding. I can use the polymers like that. So either I can use the polymer alone, or I can use polymer along with the other systems or other metals or other materials. Now the polymeric systems include the acrylics, polyamides, polyesters, polyethylene, polysiloxanes and polyurethane. Okay, so these all are the different polymers which have been widely used inside the human body for many applications. A number of processed biological materials. Okay, so these will act as a reprocessed biological materials. That means again you can keep on using it. Now the use of the polymeric biomaterials in various medical applications include a vascular graft. Where and all we can use the polymers. A vascular grafts, we can use implants and wound dressing. Okay, whenever you are dressing the wound, sutures and catheters, meshes, stents, ligament repair. Okay, we know that ligament is the structure which connects bone with the tissues. So that particular part that which will act as a middleman here. So that also is not a hard structure. It looks like almost a polymer. So you can use it for ligament repair or tendon repair, and also the valves we use for the cardiac surgeries, as we discussed in the previous slides. So for use in the biomedical applications, polymeric materials are generally classified into synthetic and as well as natural, or you can use in combination of the both. Okay, either I can go for natural biopolymers, or I can go for synthetic polymers, or I can go for both together at once, depending on the need or a requirement of the patients. Okay, so natural polymers. So here, what are natural polymers? We know that they are derived from the plant and the animals, and they may include silk, wool. We are having DNA, RNA, cellulose, proteins. What are these? These all are comes under the class of natural polymers. And then we are having synthetic polymers. So synthetic polymers are artificial or synthesized in the labs or industry. We know we are having the biodegradable and non-biodegradable polymers. in synthetic polymers, we are having non-degradable polymers also. Whereas in natural polymers, all the natural polymers are biodegradable in nature. Understanding? So here in synthetic polymers, examples can be all these. So acrylics, polyamides, polyesters, polyethylene, then polysiloxanes and polyurethane and all. Okay. And PLGA, PLA, all those things which we discussed in the previous classes, right? So that was about the polymers and their importance and their applications and some of the examples and where we will use those polymers as implants inside the human body. The next thing we are having is the ceramic based materials, where the bioceramics have certain properties such as stiffness, hardness, chemical stability and wear resistance. Whenever we need more stiffness, whenever we need more hardness and chemical stability and wear resistance, we usually go for ceramics. We avoid metals, we avoid polymers, we will go for the ceramic based materials, among others that make a highly biocompatible in nature. Ceramics are highly biocompatible in nature compared to the metals. So the most frequently used ceramic implant materials include aluminum oxides, calcium phosphates and as well as apatites and graphites. Along with the ceramics we are having apatites and the graphites also we will use. So glasses have also been used developed for medical, biomedical applications. So like glasses, glass materials and all, especially for lenses and other stuffs. Now the use of ceramics was motivated by the few things. Let's see what are those. The first thing is their inertness in the body. That means they will not react. They will not cause any chemical reaction, or they doesn't undergo oxidation. It doesn't undergo reduction. So there is no question of corrosion. So here, so inertness plays a very important role. Inertness is required for biocompatibility. What is the biocompatibility that we have discussed in earlier classes? Again, I will repeat here. Biodegradability, every biology students knows they have to degrade over a period of time whenever they lose their property. Whereas biocompatibility is nothing but when we insert something inside our body as an implant, what happens? It should not cause any harmful effects or toxicity or any rejections or any inflammations to the cells or tissues which is around this particular implant. Understanding? So for this biocompatible nature, we need to have one property, that is inertness. So ceramics has got this particular property that makes a very excellent the material, biomaterial which can be used as implants or during the surgeries. So the second thing is their formability into a variety of shapes and porosities. So we know that the metal, little bit, how much ever you want to mold, it's a little bit difficult. Whereas polymers, it's a bit easy, but polymers are, on the other hand, they are still delicate and might not get the both hardness and the mold, whatever we want. So here, when we speak about both the properties, ceramics comes into a picture. Whatever the structure we want to make, those kind of structure can be made by using ceramic materials, and we get both the shapes, how much ever you want, and as well as the hardness. So, and the third property is that their high compressive strength, that plays a very important role for their wear and tear applications, and then some cases their excellent wear characteristics, that plays a very important and makes it as a one of the best biomaterial. So selected application for ceramic includes the hip prosthesis, when you want to replace the damaged hip prosthesis, hip, so damaged tissues there, and then artificial knees, bone grafts, and as well as a variety of tissues in growth related applications in orthopedics, dentistry and heart valves. So applications of the ceramics are in some cases limited by generally poor mechanical properties. For example, it cannot bear a lot of tension, or it cannot bear a lot of load. So these two are the major drawbacks of this particular ceramics. So implant devices that are to be subjected to significant tensile stresses must be designed and manufactured with great care if ceramics are to be safely used. That means, imagine we have used the ceramics, and if that particular ceramics cannot hold so much load of a body, then it is going to break inside the human body. and that is going to cause a very severe effects. Again, you have to do surgeries and a lot of things. Whatever the effort has been put to make it as proper, that will go waste. So we, before implanting only, we must know what is the weight of the person and how much tension it might get, and how much load it might get. All these things should be studied properly. Based on that, you design the composition of the ceramics, because we know that the ceramics will come from very delicate, like a normal glasses, to the very toughest material. We can have that. We can have this particular tunability from the weakest to the strongest. That's the best property. That's the best thing about the ceramics. So that's why we need to know earlier how much load, how much tension it has to get, so that we can prepare a proper metal or ceramics. So that was about the different classification of the biomaterials. We discussed about the metals, ceramics, and as well as polymers. So next topic we are having biological and as well as synthetic materials, that we will discuss in the next class.